Different types of radioactive materials decay at all different kinds of rates. Some things last just seconds or even less. Some things last for years. But we're able to determine their half-lives following this first order decay kinetics. And so you've seen this. So this chart shows a strontium-90 isotope, and the mass is on the y-axis, and time in years is on x-axis. Strontium-90 has a half-life of 28.5 years, or 28.8 years, excuse me. And so if we plot out what those half-lives look like in terms of mass, let's say we started with 100 or 10 grams of strontium-90. In 28.8 years, we're going to have 5 grams. In another 28.8 years, we're going to have 2.5 grams, and then so on and so forth. We'll get 12.5, and then half of that, and half of that. Okay? So first order decay kinetics. The rate of decay, we use a couple of terms here. So you might see rate of decay, you might see activity. I think that is pretty common. You may also see becquerels. Okay. And what we do is we measure the activity in units of curies, which we abbreviate CI. And the original definition of the curie is the decay rate of 1 gram of radium-266, and that is equal to 1 curie, CI, is equal to 3.7 times 10 to the 10 nuclei per second. And of course, this Curie is named after Marie Curie, who studied radioactivity, studied the decay of radium, and so that's where that's all coming from. Okay, so when we're thinking back to chapter 14, which is where we initially saw rates, we would often set up an equation where the rate is equal to some rate constant K times concentration of something. And so when we're dealing with nuclear decay, rate is going to be equal to the rate constant K times the number of radioactive nuclei at time t. Okay. So again, K is the rate constant, just like we saw in chapter 14. And then N sub t is the number of nuclei at a given time. Now, this is a bit different than what we saw with rate in chapter 14, because we were often looking at maybe gases or solutions. And so we would be working in concentrations. Now we're looking at a number of nuclei. Okay, so these are going to be large numbers of nuclei. So we're going to be invoking Avogadro's number in order to come up with a value for the number of nuclei. Okay. So let's do an example, which I guess I don't know why I don't have a slide for this, but we'll do it here. Let's say we have 1 milligram of technetium-99. We saw how that decays last time. It decays, as I'm not expecting you to have memorized this, it decays by beta emission. Okay. And it has an activity of 1.7 times 10 to the minus 5 curies. So knowing this, let's determine the rate constant. What is K? So in order to do that, we are going to use this equation where the rate is equal to the rate constant times the number of nuclei. And we're going to solve for the rate constant. So I'll set everything equal to the rate constant. So K is going to be equal to the rate divided by the number of nuclei at some time t. So we need two values. We know that we have a 1 milligram sample. So 1 milligram is 1 times 10 to the minus 3 grams. And we have an activity. But we need to know rate. Okay? Rate is measured in curies, but we need to know the number of nuclei per second. And the number of nuclei is going to be measured in nuclei. So I'm going to use NUC for nuclei. So if we have nuclei per second divided by nuclei, that's going to give us a unit of 1 over S, so per seconds, which is often how our rate constant units were given, okay? 1 over time. So let's first focus on the numerator here, finding the rate. We have our activity in curies. We have 1.7 times 10 to the minus 5 curies. And we also know that a curie is equal to 3.7 times 10 to the 10 nuclei per second. And so we'll end up with 6.3 times 10 to the 5 nuclei per second for the rate. Okay, so we've gone from an activity now to a rate, and we had to use the Curie number in order to do that. But we also need to know the number of nuclei that are involved in this, and we can get that from the mass. So if we start with 1 milligram, or 1 times 10 to the minus 3 grams of technetium-99, we can use the molar mass of technetium, which is 99, and divide by the molar mass, 99 grams of technetium-99 per mole, and then use Avogadro's number. 1 mole is 6.022 times 10 to the 23rd nuclei. Typically, we've done that with atoms, right? But for every 1 atom, there's 1 nuclei, so it's the same number. All right, so multiplying all of that out, we're going to get 6.1 times 10 to the 18 nuclei. And now, because we have these two numbers, the rate and the number of nuclei, we can determine our rate constant. So we'll have 6.3 times 10 to the 5th nuclei per second, divided by 6.1 times 10 to the 18 nuclei. And we'll get 1 times 10 to the minus 13 inverse seconds. Questions on that? This isn't the most sort of typical problem that you're going to see, but I wanted to show you this because it really gets into what units we're using. We're thinking about the number of nuclei decaying away. We have to use Curies and think about what activity means. More often, you're going to be using the first order half-life equation and the first order equation that is as a function of time. I think that's how we'll say that. So for the half-life, you'll probably recall T1 half for first order is 0.693 divided by the rate constant K. So if we wanted to now find the half-life of technetium-99, because we've determined the rate constant K, we could do so. Okay. We can also determine the number or the fraction of nuclei that remain after some time t, and that's going to be the natural log of the number of nuclei at time t divided by the number of nuclei that we start with. And that's equal to minus k times t. And again, in chapter 14, we did this in terms of concentration. We did concentration at time t divided by concentration initial inside the natural log. We can't do that here because we're working with solids and concentration is irrelevant. Okay? So number of nuclei. Okay. There's also a slight variation that we'll do when we're looking at percentages, and I'll show you an example of that. Which reminds me, annoyingly, I put a set of slides on Carmen that has a few other example problems. So they are there now. When we get to those slides, I'll give you some time to grab those. I only did that right before class, so I apologize. I got distracted thinking about this demo. Oh, actually. Hang on. They left something important out. Just knock on the door. Actually, go ahead and grab those slides on that. Okay, so the next thing I want to just briefly talk about is radiometric dating, or carbon dating. This is the one that we're going to really take a look at here. There's different types of dating of older materials, but carbon dating you hear about quite often. So what happens in carbon dating is that we are essentially able to look at the amount of carbon-14 that is in a particular material, and then use that value to determine how old it is based on first-order decay kinetics. So the half-life of carbon-14 is 5,700 years, and carbon-14 decays by beta decay. So it forms an electron and nitrogen 14. Okay. So essentially what will happen is that cosmic rays from the sun, which have high energy, thank you, they enter the atmosphere and they collide with atoms. okay? And they create neutrons, and then those neutrons are captured by nitrogen atoms, which then create the carbon-14. Carbon-14 is then taken up by plants, undergoes photosynthesis, and then enters into essentially the entire food chain, makes, and more complex molecules are made. It's incorporated in lots of ways. Once an organism dies, carbon-14 is no longer being taken into the body, of course. It's not eating things, it's not breathing. And so that carbon-14 begins to decrease because of the beta emission that we've drawn here. And so based on how much carbon-14 is left, we're able to see how old that organism or fossil or whatever it might be is, okay? Now, it's limited to 50,000 years old. I don't know, are fossils older than 50,000 years? Maybe I misspoke. I don't know. That seems right? That seems too young for a fossil. Okay. Yes, so there are other ways of dating materials, such as using uranium-238 or lead-206 in rock. It's just the same process. We're able to detect these heavy isotopes, carbon-14 isotope, whatever it might be, using what we refer to, or what is used is a mass spectrometer. So mass spectrometers are able to precisely detect masses of various elements, isotopes, things like that. And so we'll make calibration curves, you've probably done that, and determine a concentration. Okay. Okay. All right, so let's, okay. Question. Strontium-90 undergoes radioactive decay to form yttrium-90. So the first thing I want you to do is write the nuclear decay reaction. So we're going to have strontium-90 forms yttrium-90. Okay, so what is the other product? Work with your neighbor and figure that one out. All right, what do we get? Yeah. An electron. Yes, so it could decay by beta decay, beta emission. There is one other option, and that is if strontium-90 were to capture a positron, it could form yttrium-90 that way. So if you came up with that, that is also valid. Okay? If you didn't, that is completely acceptable. So in fact, if we were to try to figure out which one of these happened, we could look at the band of stability, and that might be able to lead us in the right direction. The isotope, I believe, is above that band of stability, and so it actually does occur, the decay occurs by beta decay, beta emission. So let's then determine the half-life of strontium-90. So we have a 0.953 gram block of strontium-90 that weighed 1 gram 2 years earlier. So we want to figure out the half-life. I'll let you all do that for a couple minutes, and then we'll check back in. All right. So we want to determine the half-life. And in order to do that, we need to use the T1 half equation, 0.693 divided by the rate constant K. But we don't know the rate constant K. We know mass, initial mass after time 2 years, which means we have all of the information to be able to solve for the rate constant in that second equation. Now, I mentioned that n, t, and n sub 0 were number of nuclei, but because in that equation it's a ratio, so if you have number of nuclei on the numerator and in the denominators, we could go through and figure out the actual number of the nuclei using Avogadro's number, or we can just use the grams, because we're essentially going to be doing the same math all the way through. So I vote for just using the grams so we don't have to do that extra dimensional analysis. Okay, so then our first task is to determine the rate constant K. We're going to take the natural log of the mass at time t, which was 0.953 grams, divided by 1 gram, equals minus K times the time, which was 2 years. So taking the natural log, dividing by 2, we should get a rate constant of 0.024 years inverse years. Did you all get that? Okay. So are you comfortable seeing why we can use mass in that equation? Okay. You can also use percent, and we'll do that another time. Yeah. You can't use mass in the equation that says rate on the previous slide. Rate equals or k equals rate over n sub t. When you're solving for the rate constant that way, with the Curies and all of that. So that's the only time when you can. Okay, so other questions on that? All right, let's grab those other slides. Oops.